This video is on applications of derivatives. So we're going to go through a few different word problems in which we use the derivative to help us find maximums or minimums. If you are in my course, I provided you with the handout. But if not, you might want to pause the video, write down the example, and then take notes from there. So for the first one here, we say a farmer wants to fence in a rectangular area on the corner of his farm. The north side of the area backs up to a river, and the east side of the area backs up to a forest, and therefore he only wants to put up fence on the west and south sides. If he has 400 total feet of fence available, what dimensions of the rectangle will maximize the area? What is the maximum area? You might want to draw this for yourself first. If I was to draw this, it tells you that the north side of the area backs up to a river, so your river be up top here. It says that the east side, right over here, this would be the east side, there's a forest. And so we want to fence in, just the west and south sides. So this red part that I just drew in there will be the fence. And what we really want to talk about here is that, he has 400 total feet of fence. And we want to know what the dimensions, right? So we're looking for dimensions that will maximize the area of this rectangle. So I'm going to start by just saying I'll let x equal, I'll say the width, and so I'll just call it x here. Then how would I describe this remaining part of fence? Well, if there's 400 total feet of fence, then 400 minus x would equal, the length there. So this, this side here would be 400 minus x, right? Because the total amount of fence you have minus however much you gave this part should be what's left over for over here. If you were fencing in, sometimes they have the same type of example, but with two sides being the same and then one side, not needing any fence, you might need to use, 2x to take off two sides. But in this case, we have let x equal the width, 400 minus x equal the length. And now we're trying to maximize what? Well, it's asking us to maximize the area. So you really want to come up with a formula for area. Now, the area of a rectangle, you should know, is equal to length times width. And I'll call this a of x because it's really going to be a function of our variable x that we use. And we're just going to, substitute in what we call the length and the width. The length is called 400 minus x times the width, which is x. And for that area formula, I'll distribute in. Right, so we'll distribute x through here. So we end up with a of x, right? The area is equal to 400x minus x times x is minus x squared. And so we have the area formula. Now we're asked to find the dimensions that will maximize the area, find the maximum area. So if this is the area formula to find the dimensions that maximize it, I really want to, find the derivative and find the critical values of this function, and then determine if those critical values give us a maximum or a minimum. In this function here, thinking about what x represents the width. The width for x, how much fence could possibly be there? Well, there can't be less than 0. There can't even be 0, otherwise you wouldn't have a fence. So you kind of know your domain for x. If you're just thinking about this, the domain would be from 0, not including 0, up to how much total fence you have. Well, it's 400, but you can't use 400 on this side either because then you would have no fence for the other side. So the possibilities for x are only within our domain, 0 to 400. And that, is a little important when you look at these problems, making sure you have a feasible domain. So when you find critical values, you make sure they fall in that domain. So to find critical values here, we're going to take the first derivative, a prime of x. And it's equal to the derivative of 400x is just 400 minus the derivative of x squared, which makes this minus 2x. And then to find critical values, remember what you do with this, you set this equal to 0. So you set the first derivative equal to 0 or find where it's undefined. In this case, it's not undefined anywhere for real values of x, so we're okay. Solving this, I'll take the 400 and I'll subtract it from each side. So minus 400, we got negative 2x is going to equal negative 400, and then we'll divide both sides by negative 2. And so I end up with x equals 200. Now that's 200 what? Well, it's 200 feet is what we'd be talking about, because it's dimension, and they told us they were talking about feet. So it's x equals 200 feet. Now this doesn't actually give us the answer, right? This right here is just a critical value. Now, when we have an open interval like this, we only have one critical value. We know that critical value has to either be the absolute maximum or the absolute minimum. This comes from a theorem that we learned about in the last section. So now I need to test this to determine if this does give me the absolute maximum in this case. If you don't show this next part where you test it, you're not actually doing the entire problem. Because finding this doesn't guarantee you have a maximum or minimum. We have to test this. And the ways we test to see if we have a max or a min at a critical value is either by using the first derivative test or the second derivative test. I'm going to use the second derivative test because it's typically easier. It's a little more quick. For the second derivative test, you remember you need to find the second derivative. In this case, the second derivative comes from, right, the derivative of a prime. So a double prime of x, right, is equal to the derivative of 400, which goes to 0, minus 2x. The derivative of that is just going to be negative 2. And remember, when you use second derivative test, you want to substitute in the value we're talking about for our critical value. So it's a double prime of 200. Now in this case, the second derivative was constant, but it might not always be. So you want to make sure you're showing this part. So a double prime of 200, well, it still equals negative 2. The important thing about this is that this is negative. If this is negative in the second derivative, it tells you that your graph is concave down there. If I'm concave down, what kind of point is my critical value? Well, in this case, because this is concave down, we know that we have an absolute max. And that's really what second derivative test tells us. So we have an absolute maximum, right? Because the second derivative was negative, you were concave down, so it had to be a max. You have an absolute maximum at, x equals 200 feet, which is good. We wanted it to be a maximum. So it worked out in the way that the problem was kind of leading us to, but we have to show this part. So once you have that, make sure you answer the question. It says, what dimensions of the rectangle will maximize the area? Well, the dimensions, the width we just found was x. The length, well, it's 400 minus x. So, right, so we have an absolute maximum at x equals 200 feet. That's the width, right? So x equals 200 feet is the width. And then 400 minus x, which is 400 minus 200. Well, that'll equal 200 feet for the length. So you've got 200 feet for the width, 200 feet for the length. So in this case, it ended up being square. It doesn't always come out like that. They also asked us to find the maximum area. Well, what's the maximum area? The maximum area, if we're going back up here, right, the maximum area you could find from your a of x function by subbing x into here. Or you could just use the fact that area equals length times width. And since we know this, it's easiest probably to do that. Area equals length times width. So it's going to equal 200 times 200. And if you multiply those together, you get 40,000. And make sure you put units on these. 40,000. This is feet times feet, so it's feet squared. All right, and that's going to be the max area. All right, so 40,000 feet squared. So you could either substitute the length and width in like we did here, just multiply them together, or if you subbed in x equals 200, a of 200 into this, you'll get the same value. It's just a matter of your personal preference. So just making sure that you know that it could be substituted into the formula you had, or if you know the area formula, you could just do it right away. So that was the first example. Let's take a look at the next one. So the next example we have, it says from a thin piece of cardboard 20 inches by 20 inches, square corners are cut out so that it can be folded to make a box. What dimensions yield a box of maximum volume? What is the maximum volume? So making sure we know what we're looking for here, right? We're saying what dimensions, so that's what you're trying to find, and you're trying to find a formula for volume because that's what you're trying to maximize. So that's kind of how you know what formula you want to come up with. And let's just talk about what the picture of this would look like. So suppose you had this, it's 20 inches by 20 inches. So we know this is a square that would be represented by 20 inches by 20 inches. and it's saying you cut out square corners, right? So when I cut out square corners, what I'm really saying is I'm cutting out little corners like this. So then you can think about folding up the sides to make a box. So talking about the cuts I'm making, right, this is really going to help us find our dimensions. So consider that if I cut right here an unknown amount, well, that amount would be x if I cut it to there. And it has to be the same because these are square, so that would have to also be x, right? If I did it here, this would be x, right? This distance from the end to here where I cut. This distance from here to here that I cut would be x. And you could say that all the way around, right? These would all be x if you're not sure, right? We're just calling it x because I don't know how much I cut, but I'm cutting the same amount from each of the corners. They're all called x. So what I really want to know though is how do I talk about the sides, because this is going to actually be the side of the box. The part I cut out is actually the part I'm not using, right? So this part's not going to be used. This is going to be used, either as this or this, because these are going to fold upwards to create your box. Well, how long is the length that's left in the middle here? Well, each side is 20 inches. So if this whole thing from side to side is 20 inches and I subtracted out this x and this x, I really have 20 minus 2x left over for this middle part. Right? In other words, right, this length from here to here is 20 minus 2x. And it's actually the same on all the sides, right? This side here is also 20 minus 2x, and the same thing here. This length here would also be 20 minus 2x. So that's because you had a total of 20 inches and you're subtracting off x and x from each part of it. And that's the same thing you're doing on each side. So when you go to make your box, thinking about what this would look like, remember, this is going to be the sides. These parts are cut out. So you're really going to have, you know, and we'll draw it just as a sketch down here so we have it. So if I was to draw this box, it'll look something like this. All right, this goes across. This is what's going to happen when you fold up the sides. All right, and it doesn't have to be 100% accurate, just to have an idea. You've got this side here. This is the length of this side here. Let's say it's 20 minus 2x. The length of this side here would be the same as this side here, which is 20 minus 2x. Essentially, I'm just folding these along a dotted line upwards. Right? So I'm folding this along a dotted line upward. Folding this along a dotted line upward, and the same thing here. But what's the height here? Well, the height of this box is what you cut out, right? The height comes from when you fold this up. X is the piece that you cut out. So the height here is x. So drawing this is helpful because then you can get a formula for volume. Now the volume of this, you know, this box would equal the length times the width times the height. Right? That's how you're going to find the volume of a rectangular prism like this. So length times width times height. It has a square base, which we kind of knew because the cardboard was square to begin with. And if I wanted to come up with a function, v of x equals length times width times height, well, the length is 20 minus 2x times the width is 20 minus 2x times the height, which we called x. So that's a formula for volume. Because remember, we want a formula for volume because we're trying to maximize the volume, right? We're trying to find the maximum volume, find the dimensions that maximize it. So once I'm here, I would probably distribute through. It's probably easier because remember, you're going to eventually want to take the derivative of this. So I'm going to FOIL this to distribute through. And you get 20 times 20, which gives us 400. You have 20 times a negative 2x would be negative 40x. And then you get another negative 40x from the inner. So that's a negative 80x. And then the last negative times negative makes us a positive. 2x times 2x is 4x squared. And this is all still being multiplied by x here. And so I'll distribute x through this and simplify. So bringing the x through, I'm actually going to write it in descending order. So I'll actually do this one first and then work my way through. So 4x squared times x is 4x to the third power. X times a negative 80x will be negative 80x squared. And then x times 400 will be positive 400 x. So that's my formula for volume. And keeping in mind when you're doing this, right, this volume is based off of x, which is the amount you cut out of each side, right? That's what v of x is, really. It's the height, but it's the amount that you cut out of each side. So what are the restrictions on what x could be? You should think about what that, domain might be. Well, the domain on this, x can't be 0, right? It could be above 0, but it can't be 0. So it's from 0 to, well, how much could you possibly cut? Well, if I have to cut this from each side, and the total side is 20, the most you could cut from each side would be 10, but not including 10, because if you cut exactly 10, you'd be cutting it right in the middle, and then those two sides would match up. So the domain here is from 0 to 10. The important thing to recognize, though, is that you're on an open interval. Make sure your critical values only fall within that domain from 0 to 10. So when we find critical values, remember what we're doing. You want to take the first derivative, so I'm looking for v prime of x here, and that's going to leave me with 4x cubed, taking the derivative, 3 times 4 gives me 12. That's x to the second power now, minus the derivative of 80x squared is going to be minus 160x, plus the derivative of 400x is just plus 400. To find critical values, we want to find where this is undefined or where it's equal to 0. This isn't undefined anywhere, so we'll set it equal to 0, and we'll solve. Solving this, first thing you probably want to do is factor out a GCF of 4. Leaves us with 3x squared minus 40x plus 100 equals 0. And then if this factors, you should factor it. You could always use quadratic formula if you're not sure. 4 stays in front. This does factor down. For 3x squared, you should know you need 3x and x in front. You want to think of the factors of 100 in here and then use trial and error. In this case, I think 10 times 10, both of them negative, so negative 10 times negative 10 here. That does give you a positive 100. Checking the middle, 3x times a negative 10 would give me negative 30x, and then negative 10 times x would give me negative 10x, so negative 30x, and then negative 10x do give me the negative 40x. That's checking the outer and the inner when you FOIL to make sure that that middle matches up. If it didn't, that means you didn't factor it properly. Once you factored this, right, and I'm not going to go through and reteach how to factor, you want to solve. To solve this, set each of the factors that has a variable equal to 0. 4 doesn't have an x with it, doesn't have a variable, so you don't have to worry about it. So we have 3x minus 10 equals 0, and x minus 10 equals 0. Here, I'll add 10 to each side, so I got 3x equals 10, and then I'll divide by 3. Divide by 3. So I end up with x equals 10/3. On this one here, I'm going to add 10 to each side and get x equals 10. Now remember what you're finding. You're finding critical values. Right, so these would be the critical values. And then you have to make sure these make sense in the problem. Are they in our domain, and in our feasible domain? For this problem, remember I just said a little while ago, the domain is from 0 to 10. You can't cut more or even up to 10 on this, because if you cut 10 on that first cut, then you can't make a second cut, because you cut it right in the middle. So this 10 here, we actually have to reject it. All right, and the reason we reject it is that it's not in the domain. 10 is not included in the domain. So reject it, it's not in the domain. The 10/3 though, is that in the domain? Yeah, 10/3, it's between 0 and 10. 10/3, if you wanted to convert it to a mixed number, which is something people might want to do because of the applied example, that would be 10/3, 3 times 3 gives you 9, so it's 3, and then there's 1/3 left over, so it's 3 1/3. What are the units on it? Well, what are the units of x? They're based off of what you were cutting out. They were in inches, so this is going to be 3 1/3 inches. Now remember, this is not necessarily the answer. This is the critical value. You have to make sure that this critical value gives you what you need, which is an absolute maximum and absolute minimum. In this case, it's asking us to find this as being a maximum. So I want to show that this gives me a maximum. If you don't show this next part, right, you're not actually determining that it's a maximum volume. You're saying that this value is a value found for a critical value. So how do you do this? Well, we use the second derivative test, kind of like we did in the previous example. For second derivative test, you need to take the second derivative. So we want v double prime of x. Here's the first derivative right here, the 12x squared minus 160x plus 400. We're taking the derivative of that. The derivative of 12x squared is 24x. minus the derivative of 160x is just minus 160. The derivative of 400 goes to 0. Now remember what you're doing with this. You don't set this equal to 0. What you're really doing is you're substituting in your critical value. And you're determining if you get a positive or negative number. So I'm going to take b double prime of, I'm going to write it as 10/3 because it's easier to work with. These are the same exact value though. This would equal 24 times 10/3 minus 160. And 24 times 10/3. 24 divided by 3 would give me 8 times 10, so it's really 80 minus 160, which equals negative 80. But what do I care about? I care that it came out to be negative. If it comes out negative, remember what that tells you. The second derivative being negative tells you the original function was concave down. If I'm concave down, then that means I have a maximum there. And in this case, it's an absolute max because remember that critical value, if there's only one of them on that interval, either has to be the absolute max or the absolute min. In this case, that's a maximum. So this is the absolute maximum at what we just found, x equals 3 1/3. All right, so we know a maximum, the absolute maximum occurs at x equals 3 1/3 inches. And that's good, right? So we know that, but we have to answer the whole question. Right, so now we know this value will give us a maximum. We also want to make sure that once we have that, right, it says what dimensions yield the maximum volume. So this x equals 3 1/3, well, what's that? Well, that's the height, right? That's what h was, right? That's the height, right? That's this piece here. It's that part you cut out. So how do you find the other dimensions? Well, the length and the width, they happen to be the same, but you still have to go back and substitute in to get them. So, so we got this here. This is the height. And now we want to find the length and the width. So the length, which is equal to the width in this case, won't always be, but in this case they are, was 20 minus 2x, was 20 minus 2 times x, which was our 3 1/3. You might want to write it as the 10/3 just as you simplify this. So 20 minus, so the length is equal to width, which is equal to 20 minus 2 times x, what we have there. And then we're just going to evaluate that, and this will give us, it's 20 minus 20/3. 20 is really the same as 60/3, so this is like 60/3 minus 20/3, which equals 40/3, and if you wanted to write that as a mixed number, 40 divided by 3, well, 39 is the closest number to 40 divisible by 3, which gives you 13, and then 1/3 left over, so 13 1/3 inches. Right, and that's going to be your length and your width. Right, so your dimensions, if you were to write them out, and as long as you're clear about what they are, right, this is the length and the width, that's the height, are really 13 1/3 inches by 13 1/3 inches by 3 1/3 inches. And those are the dimensions that do what? Well, they maximize, right? They maximize the volume. So it makes it so the box can fit the most inside of it. The last part of the question says, what is the maximum volume? Well, the maximum volume itself, right, you could substitute into your v of x and just sub it right in, right? You could say v of 10/3. Or if you wanted to, you could just multiply these together, right? Length times the width times the height. So if we were trying to find the max volume, usually it's easier just to multiply those. I'll multiply it though as, v equals, it'll be 10/3 times 10/3 times, it's 40/3, right, times 40/3, because we're doing the 13 1/3, times 10/3, right? Length times width times height. And when we multiply those together, you end up with 40 times 40 times 10. So you're going to have 40 times 40 be the 1600 times 10. You have 16,000 over 3 times 3 times 3 is 9. So you have, or 3 times 3 times 3 is 27. Sorry, 16,000 over 27. The units on this are inches cubed because it's a volume, or cubic inches if you wanted to write it that way. That's the exact number. If we wanted to approximate this just to get you know, a nicer idea of what it might be, you could always use your calculator and do 16,000 divided by 27. I got 592.59, so we'll say 592.59 inches cubed. So, you know, this is the exact value. This is the approximation, but just so you have an idea, because, you know, if you hear 16,000 over 27, that probably doesn't give you a good idea of what you're measuring. So that would be the maximum volume that the container could hold if you made this box. All right, let's take a look at another one. So we have a soup company is constructing an open-top, square-based, rectangular metal tank that will have a volume of 32 feet cubed. The cost for the material used in the sides is 25 cents per square foot, and the cost for the materials used in the base is $2 per square foot. What dimensions will minimize the cost of the materials? So when I look at this, you know I have to talk about minimizing the cost. So I know the function I want to make is a cost function, right? And I'll call it C of x. But it's based off of what? It's based off of really the dimensions used on the sides and the bottom. It's open top. Make sure you recognize that. So there's no top that you need to include. Sometimes you will, sometimes you won't. And they tell you the volume is 32 feet cubed, and that'll be important as we do this. So if I was to just draw a picture of what this looks like, a little sketch, doesn't have to be anything huge, but just to give you an idea of what we're finding here. Right, we've got this box or this tank that's going to look like this. Again, you know, it doesn't have to be incredibly accurate, but just making sure that you have an idea of what we're looking at. So we got this tank, and they tell you that it's square based, which means that the box is a square at the bottom, right? So I'm going to call, you know, the length of this side x, and I'm going to also call this x, because if it's a square base, then it has to be a square on the bottom. So we have x times x. And then we have some sort of height, and they don't tell you anything about the height, so we can just call that, I'll call it h. So if I was talking about the volume here, just based on the variables I use, the volume of this would equal x times h, right? Length times width times height. So that'd be x squared h. Now we also know that the volume, they told us the volume is 32 feet cubed. So I know that we have x squared h equals, right, 32 feet cubed, or 32 for what I'm doing here. The reason I'm doing this is that I want to, you know, I have two variables here. I want this all to be in terms of one variable. So to make this all in terms of one variable, what I'm going to do is I'm going to solve this for h, and that's why they really gave you the volume, so you're able to solve this for h. So I'm going to divide both sides of this by x squared, so I can get h in terms of x. So h is really equal to 32 over x squared, and that's really how you can kind of think about it when you're approaching this problem. This is equal to 32 over x squared. All right, so that's why they gave us the volume, so we could make that connection. Now, when we're looking at this, the cost of it is really based on the surface area of the materials being used. So the surface area formula, you know, would be just adding up all the faces of this that you're using, but you have to take in mind the cost for each of those as you're doing it. So if I made a function called c of x, being the cost function, it's equal to the cost for the four sides, right? So just if I was saying it, the cost of the four sides, I'm just saying it in words, right? Plus the cost of the base. So it's the cost of all the sides going around, plus the cost of whatever the bottom cost to make. And that's how you'd find the cost of this. Well, let's talk about what the cost of the four sides would be. Well, the sides are 25 cents per square foot. So we know that it's 0.25 times, well, how do you find the square feet for each of the sides? Well, for one of the sides, right, the area of one of these faces is just the length times width, or x times h, and so in this case, the length times the height. So x times h, right, and that's the area of one of them, but how many are there? Well, there's four, so it's times 4xh. The x times h gives you the surface area for one of the sides. There's 4 of them, so you're doing 4 times xh. The 0.25 here is the 25 cents times the amount of material you're using for them. All right, plus the cost of the base. Well, what's the base cost? Well, it costs $2, so it's 2 times, and then the base, the area of the base is just going to be this flat square at the bottom. It's going to be x times x, so that would be x squared. There's only one of them, so you don't have to have a number in front. If there was a top, you would have to make this 2 times 2x squared, because then you would have another square top. So, you know, this is the function for the cost. If they only wanted you to maximize or minimize the surface area, you would not have the costs in here. You would just say the 4 sides is 4 times x times h for the area, for the surface area, and the cost of the base would be x squared. But since they asked us about cost, we're taking it into account. Let's simplify this formula. So we have the cost is equal to, well, 0.25 times 4, that's going to give us 1. So it's really just going to give us xh plus 2x squared here. And then the last thing is, I want this to be a formula just of x. Well, right now I have this in terms of x and h. Well, that's why we did what we did earlier, right? The volume here, we wanted this h equals 32x squared, right? We're going to use it here to make this cost function be all in terms of just x, because now I can write this as c of x is equal to x times, what's h? Well, h is 32 over x squared plus 2x squared. And then I can say this cost function is equal to, just simplifying it, canceling one of these x's in the denominator with this x here, I'm left with 32 over x plus 2x squared. And that's the cost function, that's c of x. Now, that was just coming up with the function. You know, I kind of took my time going through it. But once you have the cost function, what do we want to do with it? We want to, it says, minimize the cost. So if I want to minimize the cost, I have to take this, find critical values, and then determine if the critical values are maxes or mins. So first thing I want to do is now I'm going to take the derivative of this. So before I can take the derivative, I have to rewrite it. Because, you know, you want x's to be as powers in the numerator. You can't have them in the denominator to use our power rules. So we're going to first rewrite c of x, the cost function, as 32x to the negative 1, right? That's how you're going to move that up to the top, plus 2x squared. All right, and then we're going to, as we do this, take the derivative. So c prime of x is equal to, taking the derivative of the first term, negative 1 times 32 is negative 32x to the, subtract 1 from the exponent makes that negative 2, plus 2x squared, bringing the 2 down, makes this 4x for that derivative. So I got negative 32x to the negative 2 plus 4x. Remember what you're doing with this, you're trying to find where this derivative either comes out to be undefined or equal to 0. Let's make sure we simplify it so we can see this. So c prime of x is really equal to negative 32 over x squared plus 4x. And we do actually have to consider, where does this not exist? Well, when x is 0, right, this derivative doesn't exist. It would be undefined there. But x can't be 0 because x is a dimension of this box, right? So we know x doesn't equal 0. We know x has to be a positive value. So we know that we don't have to worry about that as being a potential critical value in this case. For where this equals 0, you do want to set this equal to 0 and solve. If I set this equal to 0 and solve, the first thing I want to do is multiply through by an x squared to each side. This way I can clear fractions. So if I do that, right, I'm multiplying x squared times negative 32 over x squared plus x squared times 4x equals really x squared times 0. What I'm really doing here is you multiply each side by x squared. To clear fractions, multiplying by the LCD, remember. And the reason we're doing this is so we can work with this a little easier. So the x squareds cancel here. I got negative 32 plus x squared times 4x is 4x to the third power. And then this is equal to 0 times x squared is still just 0. We want to solve this. To solve this, I'll add 32 to each side. So I end up with 4x cubed equals 32. And then we want to divide both sides by 4. So I'll divide by 4 and divide by 4. So I get x equals 32 over 4 gives me 8. Oh, sorry, x cubed equals, right, 32, or equals 32 over 4, which gives me 8. So x cubed equals 8, canceling the 4's on the left. And then solving this, remember what you want to do. You want to take the cubed root of each side. If I take the cubed root of each side, I get x equals the cubed root of 8, which is 2. Now remember what 2 is. 2 is the x value is a critical value, and this is measured in feet because the container was measured in feet. Or feet cubed, I should say, for the volume. So x equals 2 feet. Now remember, this is the critical value, but it's not necessarily what's going to give us the minimum cost. We have to determine, is the cost a minimum here? And the way we do that is by second derivative test. So right now you found the critical value, but you need this next part. All right, so the next thing you need to do is the second derivative test to determine, does this give you an absolute maximum, absolute minimum? It's the only critical value we have on our interval, so we know that if it does give us one or the other, it is the absolute maximum or minimum. And then substituting in to the second derivative, we first need to find the second derivative. So I need c double prime of x. Well, I'm taking the derivative of c prime. I'll use this form right here because remember you want your x's to be in the numerator. So the derivative of negative 32x to the negative 2 would make this a positive 64. A negative times that makes that positive 64. X to the negative 3. Plus the derivative of 4x is just 4. Now remember what I'm doing. I'm substituting in 2 for x to see if it gives me a maximum or a minimum. So c double prime of 2 is equal to 64 over, when I say x to the negative 3, it's really like x to the third in the denominator. So I can say it's 64 over 2 to the third, right? Subbing in for x and then moving it down to the bottom. Plus 4. Evaluating this, 64 over 2 cubed is 8. So 64 divided by 8 is going to give you 8 plus 4, which equals 12. What's important about that? Well, the important thing is that this is positive, right? So second derivative test, I want to know if this is positive. If the second derivative is positive, what's the concavity? Well, it's concave up. If it's concave up, that tells you that your critical value, that's going to be an absolute, because there's only one critical value, and it's going to be an absolute minimum because it's at the bottom. So we have an absolute minimum at x equals 2 feet. So that's the x value, right? They asked us to find the dimensions that will minimize the cost. Well, that's the x value. How do I find the height? Because we got the x value, so that's the length and the width is, 2 feet and 2 feet. And then what's the height going to be? Well, the height of this container from here, then you would say the height is equal to, right, is what h was equal to 32 over x squared. Right, so the height equals 32 over x squared. That's coming from up here, which came from our volume. If you don't do this first part with the volume, you're going to have h's in this problem, and it's not going to take the derivatives correctly. So you have h equals, you have 32 over x is 2 squared, so that's 32 over 4, which gives us 8, so that's going to be 8 feet. So the dimensions that minimize the cost would be 2 feet by 2 feet by 8 feet, right? So our dimensions here to minimize the cost would be 2 feet by 2 feet by 8 feet. That's looking at what we had in this, 2 by 2 by 8. Now, if I asked you what the cost was, right? So what is that minimum cost? You would actually substitute into here, right, for c of x, you would sub in c of 2, right? And you could actually evaluate it. So they didn't ask us for it, but just maybe because we want to talk about it, the minimum cost, all right, so the minimum cost would be equal to c of x, which is 2, and that would be 32 over 2 plus 2 times 2 squared. So that's 16 plus, this is 2 squared, 4 times 2 would give you 8, so plus 8. So that equals $24. So the minimum cost for the container with those dimensions would be $24. You know, if the question just asked you about surface area, like I mentioned earlier, and they didn't ask you about minimizing the cost, but actually asked you to minimize the surface area, you wouldn't include the prices on this, and then you would just get the dimensions that way. But they would be different dimensions because the cost has an impact on this. So those examples all had to do with finding maxes or mins, using derivatives when you had, you know, one critical value, so you knew it was an absolute max or an absolute min. This next example we'll talk about has to do with manufacturing, but it's still the same type of idea. It's actually probably a little easier to handle. So we'll look at this last one here. So we have a stereo manufacturer determines that in order to sell X units of a new stereo, the price per unit in dollars must be this. P of X equals 1,000 minus X. So that's the price in dollars to sell X units, right? So X is units, P of X is the price. The manufacturer also determines that the total cost of producing X units is given by C of X, which is equal to 3,000 plus 20X. So this is the cost for producing X units. And then they ask you a few things. So the first one says find the total revenue R of X. So we'll do this here, and then we'll work our way through the rest of it. So R of X, well, how do you find revenue? Well, revenue is usually in words would say the price per unit times the number of units sold, right? That's how you get revenue. You sell something for a certain price and how many of them you sell, and that will multiply together to give you the total amount of money you're bringing in. In this case, we know what the price per unit is. They told us it's this function here, P of X, so it's 1,000 minus X. So it's 1,000 minus X times how many units are you selling? Well, you're selling X units. So then we just distribute through, and you have a function R of X is equal to 1,000x minus x times x is x squared. And that's all we're doing. We're finding the function. That's all it asked us to do. Part B says to find the total profit, P of X. Well, P of X, the profit, remember, if I was doing the profit is equal to what? Well, it's equal to the revenue, all the money you bring in, minus the cost, how much it costs you to produce. And we just are going to fill in with what we have. R of X, we know, we just found the last example is 1,000x minus x squared, minus C of X. Well, C of X is this 3,000 plus 20x. And you want to make sure when you're writing that, you have parentheses around it because that negative belongs to all of it. And then we'll distribute the negative through here. So we would have, this is 1,000x minus x squared. A negative times a positive makes this negative 3,000. A negative times a positive 20x makes that negative 20x. So my P of X function is equal to, in descending order, I'll have negative x squared. And then we have 1,000x minus 20x, so that'd be plus 980x, and then minus 3,000. So that gives us our profit function. Remember, profit is just revenue minus cost, and then we're just simplifying it. Part C says, how many total units must the company produce and sell in order to maximize profits? Well, if you hear that word maximize in there, or minimize, remember that means you're trying to find the derivative of whatever they're asking you to maximize or minimize, and then determine the critical values, and then determine if it gives you a maximum or minimum. So that's what we'll do. So part C here, all right, means, you know, to maximize or minimize a function, we have to find the derivative. So P prime of X, in other words, what I need first. And the derivative here of negative x squared would be negative 2x, plus the derivative of 980x is just 980, and then minus 3,000, derivative of that is 0. So we got negative 2x plus 980 equals the derivative. When you do this, remember when you take the first derivative, you want to find where it's equal to 0, where it does not exist. In this case, you know, it's defined for all x values. Remember, our x's here are on an interval from 0 to infinity, because we're talking about items produced, right? So solving this equal to 0, I'll subtract 980 from each side. Subtract 980 here. and that gives us negative 2x equals negative 980. Divide by negative 2. Divide by negative 2, you get x equals, this is positive 490. And that's what? Well, that's units, right? X equals 490 units. Make sure you give me, that you're finding the units of the stereos. So x equals 490 units. That doesn't tell us anything yet. We're trying to find the number of units to maximize profits. I have to prove that this is a maximum. Well, because we're on an open interval from 0 to infinity, right? We have one critical value, right? This is our critical value. We can use our second derivative test to determine, is this a absolute maximum or absolute minimum? Second derivative test means you need the second derivative. So p double prime of x. Well, the derivative of negative 2x plus 980 is just negative 2. And we want to look for p double prime of 490. So we know that this is a constant, so it'll always be the same, but you should really show it to show that you understand that we're looking at p double prime of the critical value of 490. It still equals negative 2 because there's no x value to substitute in for on the left because it was a constant, or on the right because it was a constant. But what does this tell us? Well, if this is negative, right, the second derivative being negative, it tells you that you're concave down. If you're concave down, then that tells you that your critical value is going to be an absolute max at that point, right? Absolute because we're on an open interval and we have one critical value. Absolute max because remember concave down at that point puts it up at the top, right? It's a peak, so absolute max at x equals 490 units. All right, so that was part C. How many units did you have to produce? 490 is the answer. This is what shows it down here. The last two parts says D, what is the maximum profit? Well, you found the 490 units you just needed to produce. So for part D, all you're doing with this is saying we want P of 490. Make sure you're using capital P, the profit function, right? That's P of X that I'm talking about here to find the maximum profit. It's not this lowercase p of X, which is the price, remember. That was a different function. So P of 490, you're substituting it into here. You end up with negative 490 squared. The negative's on the outside of that. The 490 is getting squared, not the negative, right? Because you're substituting into this down here. So negative 490 squared plus 980 times 490 minus 3,000. And you're going to evaluate that. We can do it on our calculators. So we have negative, and then the 490 is getting squared, not the negative sign. So if you write it like that, that's what that really means. If you wanted to, you could put parentheses just to be sure. So you could write it as negative parentheses 490, close the parentheses, square on the parentheses, plus we have 980 times 490 minus 3,000, and that'll give us, we got 237,100. So this will be 237,100. What is this? Well, it's dollars because we're talking about profit, and this is the max profit. All right, so this is the maximum profit. That's what they're asking us to find there. So this is the maximum profit. And then the last question says, what price must be charged per unit in order to maximize profit? Price, well, they told you price is this P of X function up here. We want to use it when maximizing profit, so that'd be P, lowercase p of 490, and that's just that function they told us at the top, the 1,000 minus X. So it's 1,000 minus 490, and this will equal $510. And this is the price, what? It's the price, right, per unit. So if the price per unit, it's $510 per unit. So hopefully these examples helped in learning how to do problems where they're asking you to maximize or minimize a quantity. Just keeping in mind that you do have to show that what you found for your critical value does provide the maximum or the minimum. And we did that mostly with second derivative test. You could also use first derivative test for that. But if you're not showing it that it actually produced a maximum or minimum, it doesn't actually, show that you do have that. So you have to use the calculus to show that.